So this is the note for the supplementary for the chapter 32 for the Maxwell equations. Actually, in the textbook, it does not mention about the differential form of the Maxwell equation, but I think it is quite important. Okay, without that, we cannot really derive the electromagnetic wave in the coming chapter. Okay, so I just spend some time to introduce these parts. Okay, so this is the outline. We'll introduce the differential form of the Maxwell equation. Okay, and then I will introduce two theorems in the multi-variable calculus. One is called the divergence theorem, or called the Gauss theorem. Okay, and another one is called the Stokes theorem. Okay, and based on that, we can really derive the differential form of the Maxwell equations. Also, we can mention about the conservation of charge using an equation. Okay, and it will tell you that in chapter 29, we only learn the Ampere's law with one term on the right side, only mu naught I enclosed on the right side. But in chapter 32, it also tells you that after adding a term called the displacement current, and then it will be more correct. Okay, you may ask whether we need to add the third term or the fourth term to it to make it even more correct. The answer is no, because at this moment for the Ampere-Maxwell's law, it already satisfies the conservation of charge. If we further add more to it, then the conservation of charge will not hold anymore. Okay, so it will also tell you that the Maxwell equation at this form will be compatible to the conservation of charge. Okay, so up till now, what we have learned is like this. Okay, so in chapter 23, we learned the Gauss law. In chapter 32, we learned the Gauss law for the magnetism. Okay, and then in chapter 30, we learned the Faraday's law, and then in chapter 29, we learned the Ampere's law, like this, and also this term in chapter 32. Okay, so we have learned these four equations called the Maxwell equations. Okay, so for the first two, they look similar. Okay, this is both of them are surface integral for the E field and B field. On the right side, Q enclosed over epsilon naught. Epsilon naught is a constant. And then on the right side, as much as we don't have magnetic monopole, okay, so for the second one, it should be a 0 on the right side. And then for the third and fourth, okay, they look similar. Both of them are line integral. Okay, the third is E dot ds, and then the fourth one is B dot ds. Both of them are line integral for a contour or for an Ampere loop. Okay, on the right side, the derivative of the derivative of 5b. Okay, and then take the minus sign. Okay, which means that if we have a changing magnetic flux for the loop, okay, and then it will generate E field. And then for here, if you just ignore this part, if we have a changing E field, it will generate magnetic field. And of course, this static current will also generate magnetic field. But this one, if this I enclosed is not changing, then B is not changing. Okay, then it will not further generate induced E field. But if this d phi E, the rate of change is not a constant. If this is not a constant, then it will generate the B field, which is also time varying. And then this time varying B field will further generate E field. And then this E field will further generate, okay, looping back and forth. Okay, so it will form the electromagnetic wave. Okay, so here, okay, we try to change some of the notation. Okay, first of all, we will try to change this 5b change this phi b back to an integral form. Okay, so this is nothing special. Similarly, this phi e, we also try to change it back to an integral form. So nothing special here. Okay, it's just a phi b equals integration of a b dot dA. And then also, this is nothing but a phi e equals integration of a e dot dA. We just try to change it back to the integration so that you can see b, e, e, b. Okay, because phi b is just a function of the b, so yeah, we just make it more explicitly. Okay, so the next is we try to change the notation back to this form. Okay, of course in this textbook it always use a single integration sign. Okay, so that something like this e dot dA, and then something like integration of e dot ds. But this is a line integral, this is a surface integral. Okay, so actually they should not be look alike, but they only use this like a dA ds to specify all the things, or whether it is 2-dimensional or 3-dimensional, or only 1-dimensional or 2-dimensional. Okay, but actually for some of the mathematical textbook, they will use let's say we have 2 integration sign for a surface integral, because this is 2-dimension. This is 2-dimension, and then also this one, this is a surface integral, so we use 2 integration sign, and then also this one, the e dot dA, this is double integration sign. But for this one, this is a line integral, so ds is in a single dimension, so we use a single integration sign. Okay, other than that, we also try to change this one. Okay, the q enclosed will change to the triple integral of rho dot dv. Okay, rho dot dv. So it looks so horrible, but what does it mean? So I think in maybe primary school or high school, okay, you learn something like m equals rho times v. Okay, so the mass equals the density multiplied by the volume, something like that. Okay, so at that time we assume that the density is uniform. So that something like this is simplified to a multiplication. The integration simplified to an integration. But if the rho is not uniform, then in different location, then we really need to consider, or suppose this is the object. Okay, and then we will try to find the total mass with the rho of r. Okay, suppose rho of r. Okay, so suppose we only know rho for the whole thing. Okay, we know how it distributes. Okay, so if we would like to find the total mass, which means that we would like to calculate rho times dv. dv is the small volume. We assume that inside that small volume, vol is a constant. Okay, so in that case, we can have rho times dv. Okay, actually this is a scalar. Okay, so we only have a multiplication. Okay, this is just a multiplication, and then we need to add many of them together, so that finally turns out to be an integration. Okay, but actually this volume is in 3-dimensional, so we put 3 integration sign there. Okay, so it just look like that. Okay, so in that case, similarly, we have a q. The total q is analogy to the mass. Okay, this surface, this volume charge density, like this density. Okay, and then dv. Okay, like this one. Okay, so we have a Q enclosed equals the triple integral of rho times dv. Okay, also we have this one, this I enclosed. This I enclosed we can also change it to double integration of j dot dA. Okay, of course in chapter 26 we already know that I equals integration of j dot dA. But here we just change this one to double integration sign because this is dA, this is in 2 dimensions. So I think we somehow explain how we change the equation from previous page to here. Okay, so we change this one. We change the number of integration sign, and we also change this I enclosed. Okay, nothing else. Okay, so up to this moment we have this 1, 2, 3, 4. Okay, so next we would try to introduce what is the conclusion, what is the differential form, what is the differential form of the Maxwell equation. The answer is the Gauss law for electricity look like this, Gauss law for magnetism look like this, the Faraday's law look like this, the Ampere's law look like this. Okay, so if you are clever enough, you may find something like, we can try to change this one, this double integration sign to something like this, okay, and then this line integral, we change it to something like this. What does it mean? So far you don't know yet, maybe, but at least you can consider, okay, we have learned this sign is so-called a gradient. You also know that this is the inner product, this is the cross product. Okay, so actually that has that meaning, but if we have this one and this one, okay, they have another names. Okay, so yeah, I will explain it slightly later. Okay, but actually for the differential form it look like that, and then also you can see that for this triple integration sign we just it just disappear. Okay, it just disappear, so it remains this 1 over epsilon naught rho. Okay, so which is rho over epsilon naught. On the right side here is 0, so it's just 0, and then for here, okay, the integration sign just disappear, so we only have a dB dt, but b is a function of x, y, z, and t, so this is a multi-function, multi-variable function. Okay, so we use the partial derivative rather than the original derivative, or the okay, and also here, this double integration sign disappear, this double integration sign disappear. Okay, so it turns out to be mu 0 j and then plus epsilon naught partial e partial t, something like that. Okay, actually we will use some more mathematics to derive that rather than just a conversion, but yeah, sometimes in the physics many equation we can use this kind of like the quick trick to convert the things. Okay, but actually I think you don't need to remember that. Okay, at least I will I'm not sure whether I'll giving in the formula sheet for the exam, but anyway, I don't think any problem will be related to that part. Okay, so actually when we try to summarize the Maxwell equation for the integration form and the differential form. Okay, the integration form look like this. After the slightly modification for the number of integration sign and also the Q enclosed, the I enclosed. Okay, and I would say this is actually the first source for the equation, and then this is the second source. Okay, in the Maxwell equation we only have two sources. One is this charge, and other one is this current, and the other one is this current. Okay, after considering these two, then, or I should say, after providing these two information, you will be able to solve what is the E field and B field in the space and time, okay, after giving you these two. So these two are called the source or the input or the, and actually in the next chapter, when we introduce something called the free space, which means that there is no source, which means that we try to make rho to be 0 and also j to be a zero vector, okay, for the free space in the next chapter. So yeah, something like that. Yeah, suppose for some guys, they try to design the antenna 设计天线的话 okay, they try to design the shape of the antenna so that it try to guide the current how to going through the conductor, okay, so it will form some shape of current or the current density, and then based on that it will generate some electromagnetic wave, and then they will try to guide it to probably one dimension. For example, if you have a smartphone, okay, if you try to measure how it generates the EM wave, I will tell you that suppose this is the monitor, okay, this is the other side, okay. So in that case, the mobile phone, the smartphone will try to generate the EM wave in this direction, in this direction, rather than that direction. The idea is simple because if you try to, probably you need to talk with your phone like this, okay. If you just try to generate the energy in this direction, okay, all the energy will go into your head. Okay, this is not good for your health. So, and also your head may absorb some of the energy. So it's also not good. So in that case, they will try to design the antenna, try to propagate the energy in that direction to the outside. Okay. Okay. So yeah. So this is how we can use the Maxwell equation. Of course, this is not easy. Probably all these equations you cannot do much hand calculation to it. Yeah, probably if someone will use it, probably use it for computer software to use some numerical method to solve for the E field and B field. Okay, so this is a quick summary. I have not tell you how we can derive the differential form yet from the integration form. Of course, the integration form is not come from derivation. It is just a law. When I introduce all this law to you, I just tell you this is a law. Okay, the physician try to summarize Gauss, Faraday's, Ampere's. Okay, fine. Okay, this equation will satisfy the true condition. Okay, so yeah, it's just like that. Okay, but actually from the integration form to the differential form, we can use some more rigorous mathematics to really derive these equations. Okay, so first of all, before we try to derive them, I would introduce two things. One is called the divergence, and another one is called the curl. Okay, so for the first one is the divergence. Okay, just now I mentioned we have a symbol like this. Okay, called the okay, so it is actually called divergence. And then just now I mentioned, okay, this is a gradient. This is an inner product. Okay, so this is actually like this. Okay. Okay, so if you still remember in chapter 24, we have learned the gradient operator. At that time, we learned it as E equals negative gradient of V. Okay, if you still remember. Okay, so actually this gradient in Cartesian coordinate is like partial x, partial x, I vector, I is the unit vector in x-axis, partial y, j hat, plus partial z, k hat. Okay, this is the gradient operator. Okay, so actually for the divergence operator, you can consider it as this gradient operator dotted with another vector. Okay, so it should be operate with another vector or vector field. Okay. So yeah, so suppose we have a vector field called F. Okay, of course we don't have F in this equation. It can be E or B, but I try to make it F. Okay, so actually you can just replace F to E or F to B. Okay, so it so that it is suited for both this one and this one. Okay, so suppose we have a vector field F in Cartesian coordinate like fxi hat plus fyj hat plus fck hat. Okay, so the divergence in the Cartesian coordinate. Okay, so all of them are in Cartesian coordinate. If it is in other coordinate system, the form looks quite different. Okay, quite different. Okay, and actually it is hard to remember. I have never remembered them. Yeah, but actually if you really need to derive it, it takes a much more complicated mathematics like the tensor algebra to really derive it correctly. So yeah, it might be too difficult, but for Cartesian coordinate it is not that difficult. It's just like 1 times this one, 1 times this one, 1 times this one. Okay, so yeah, so actually the divergence of f looks like partial fx partial x plus partial fy partial y plus partial fz partial z. Okay, looking like this, very symmetrical. Okay, so actually the idea is like this one is nothing but the gradient operator is like partial x I hat plus partial y j hat plus partial z k hat, and then dotted with fx I hat, and then plus fy j hat plus fz k hat. Okay, so this is a dot product like a multiplication, so we need to distribute. Okay, so we all together should have 9 terms, but hopefully 6 of them are 0. Okay, 6 of them are 0. 6 of them are 0. Okay, why? Okay, because if we try to consider this one, okay, we try to distribute this one dotted with 1, 2, 3 terms. Okay, so for the first one, partial x I hat dotted with fx I hat. Okay, if you still remember, I hat dot I hat is 1. Okay, so yeah, so the remaining things is partial fx partial x, so which is correspond to this term. Okay, so the remaining 2, I hat dot j hat will be 0. Okay, sorry, I hat dot j hat is 0. Okay, this one, I hat dot k hat is also 0. Okay, so these 2 goes to 0. So the remaining 2 is like this one. Okay, with this one. Okay, so j hat dot j hat. Other one are j hat dot I hat will be 0. J hat dot k hat will be 0. Only j hat dot j hat will be 1. So we have a partial fy partial y. Okay, which is actually this one. And finally we have this one dotted with this one. So we have a partial fc partial z to be this one. Okay, so it's somehow something like that. Okay, so this is the divergence operator. Divergence operator, what is its physical meaning? For the divergence operator, it tries to consider whether the vector field. Okay, remember this is the vector field. The vector field means in the whole space, yeah, it's just like f is a vector. And also, we also have this, let's say this is R. Maybe this R hat is something like XYZ. Is XYZ. Oh. Okay. So this argument is also a vector. It's also a vector, which means that in the whole space, given the coordinate, let's say this in the original point 0, 0, 0. If you substitute x to be 0, y to be 0, z to be 0, and then you can find this is a vector. And then at the other point, let's say 1, 1, 1, and then you plug in all this 1 to the xyz, and then you can also find f to be another value. But actually, it is still be a vector. So all the way to be a vector, just like the E field in the space. Suppose you put a charge. Let's say that you put a positive charge there, then it will generate E field all pointing all the way outside. So yeah. So actually, when you try to put in some coordinate, okay, so let's say this is xyz to a specific function, okay, let's say E hat, okay, so this is called a vector field, okay, it is defined on the whole space, and then the value is a vector, and then the input is also a vector. This is the R, okay. So actually, the divergence tells you that for this vector field, whether the vector field is going outside or going inside. Okay, so for a specific point, if if the divergence is larger than 0, which means that the vector field is going outside. If this divergence is negative, then it means that for that point, okay, actually this one is for that point only. For the other point, actually they are all 0. And for this point, okay, actually it is for this point only. So you can see that for this point, all the vector field, all the vector are pointing to that point, going in that point. Okay, so it takes a negative value, similar to what we have done for the Gauss law. For the Gauss law, we always consider dA is pointing outside. So if something like integration of E dot dA is positive, then which means the net flux is going outside. The net flux is going outside. We correspond to this case. And then if this one is negative, then it corresponds to that case. If it is 0, correspond to this case. Just say, okay, so given any point, okay, the vector field, okay, going in, going out, just cancel each other. Okay, so this is actually the divergence. And then next is called the curl. Okay, it looks a little bit more complicated. At least it has totally 6 terms. Okay, so still you can consider it is like a gradient operator cross with a vector field f. Okay, so we have this gradient operator cross with this vector field f. Okay, so yeah, so for the cross product in the Cartesian coordinate, yeah, we can, actually we can just distribute. Like what we done before for the multiplication. Okay, so you can just distribute. Okay, this term distribute to 3 terms, and then altogether we have totally 9 terms. But if we have only 3 dimension, we can use this trick to really calculate the cross product. Okay, so this is called the determinant. Determinant 行列式. Okay, so to calculate determinant, okay, if it is up to 3 times 3, it is still easy. Or if it is 2 times 2, it is even more easy. Or if it is something like A, B, C, D, the determinant is nothing but AD minus BC. But if it is for 3 dimension, it should have 6 terms. If it is 4 times 4, it altogether have 44 terms. So which means if we have n times n matrix, and then you need to calculate its determinant of an n times n matrix, then it will have n factorial terms. So up to 3 times 3 it is still easy. 3 times 3 is 3 factorial, which is 6. Okay, so the idea here is like you try to calculate in this direction. Okay, this direction. So you have I hat partial y and then fc. Okay, so you can try to find where it is. I hat is here, partial y fc. So this is actually the first one. And then let me try to change another color. So okay, the next one, j hat. Okay, so you should go to here. Okay, j hat partial z fx, j hat partial z fx. Okay, this term. And then try to change another color. Okay, so we have a k hat, and then these two, k hat partial x fy, k hat partial x fy. Okay, this one. Okay, so I try to use the highlight for another direction. Okay, for another direction, we go like this, and then go like this. Okay, I had partial z fy, I had partial z fy. But in this direction, we need to put a negative sign. Okay, so next we have j. Okay, j hat partial x fc, j hat partial x fc with a negative sign, which is this one. And then finally we have this one, k hat partial y, k hat partial y fx, okay, with a negative sign. Okay, so we all together have 6 terms. Actually, we can try to distribute, and then you will find the same answer. Let's say if we have this one, distribute. So for the first one, I hat cross I hat will be 0. I hat cross I hat will be 0. So the first one is 0. And then for the next one, I hat cross j hat will be 1. Okay, will be positive 1. Okay, so we have positive 1 times, no, sorry, not positive 1, positive k. Okay. For the second one, we should have I hat cross j hat to be k hat, positive k hat. Okay, so it turns out to be partial fy partial x with a k hat. So it goes to here. And then for the third one, I hat cross k hat. I hat cross k hat will be negative j hat. Okay, so it is a negative j hat and then partial fc partial x, which is going to be here. Okay, j hat partial fc partial x. Okay, so I do not go for the others, so you can try to practice it yourself if you have interest. But actually, this way can also give you a correct answer. Okay, so anyway, the curl look like this. Yeah. Okay, so what is this? What is its physical meaning? So the curl means how the vector field is rotating across a point. Okay, so let's say if we have a vector field like this, let's say f hat x y z to be y I hat minus x j hat. Okay, without k hat. Okay, so it don't have the third dimension. Okay, so this is the x-axis. This is the y-axis. Okay, so let's say we can try to substitute some point in that. Let's say if it is 0, 0, 0, okay, 0, 0, 0, which means that at the original point, it should be a 0 vector. So at the original point, it has nothing. Okay, At the original point, it has nothing. Okay, let's say if it is 1, 0, 0. 1, 0, 0, 1, 0, 0 means this is 0. This is 1. Okay, so which is a negative j. If it is okay, let me try to write it out. Okay, if it is 0, 0, 0, it turns out to be a 0 vector. If it is like a 1, 0, 0, it turns out to be a negative j hat. Negative j hat, which means some point around here. Okay, you can see this arrow is around here. It's around here. Okay, so you can see a pointer pointing downward, which means that this is the negative j hat. So let's say if it is 400, okay, it turns out to be a negative 4j hat. Okay, so you can see negative 4j hat is here. Okay, so you can see this error is larger. This is larger to specify a stronger vector at that point. Okay, maybe let's try to consider one more point. Let's say it is 440. 440 means this is 4, this is 4. So it is 4i hat minus 4j hat. Okay, which is 440 is around here. Okay, around here. Oh, sorry, it should be something like 440. 440. This is 440. 440. Oh, let me see. 440. That is correct. Okay, so yes, so you can see this vector is like this. Okay, this is 4i, this is negative 4j. Okay, so this is correct. This is correct. Okay, so you can see. Okay, so actually you can arbitrarily try to plug in some coordinate into this expression, and then you will find a corresponding vector. Okay, so if it is a longer vector, then it means that the magnitude at that point is larger, and then also the direction also specify how is the direction of the vector at that point. Okay, so actually if we try to calculate the curl of f, okay, you try to plug in this expression to there, which means that this is actually f of x. This is actually f of y. F of y is negative x. F of x is y. F of x is f sub x is y. F sub y is negative x. Okay, and then f sub c is 0. Okay, and then you try to plug into here, or if you try to plug in here, it's also okay. So in that case, you will find that the curl of f is actually negative 2k. I don't try to going deep into it. Okay, actually you can see this will give you a negative 1. This one will also give you a negative 1 for the k vector. Okay, so it turns out to be negative 2k. So what is it negative 2k mean? Negative 2k means it is actually rotating in according to this axis. Negative 2k. Okay, this is x-axis. X-axis is pointing to the right side. Okay, right axis pointing upward. Okay, so using a right-hand rule, the z-axis is pointing out of the page. Z-axis is pointing out of the page. Okay, so which means that this is negative 2. This is the unit vector in z-axis, which means that this is pointing into the page. So curl of f curl of F is actually pointing into the page. So using the right hand rule, you use a thumb pointing into the page. Your finger will follow the direction of the vector field, Okay, so that's the idea. Okay, so this is actually the rotational axis. Like the torque. The torque is also a vector, and then how it change, how the object is rotating is according to the rotational axis. So here it is also like the rotational axis. Okay, so in that case, this means that the vector field is rotating clockwise and along the z-axis. Okay, this is a negative z-axis. Okay, so this is a curl. Okay, so let's have a 10 minutes break and then